Welcome to the Sydney branch of the Royal Aeronautical Society's first webinar, which will be one of many coming up in the future, we hope. The reason I mention it's the first time is just bear with us. We're learning the ropes as we go. It's actually the second one the Society's run in Australia. Melbourne ran one a few weeks ago, very successfully. And we are hoping to be able to have an offering to our national membership every 2 weeks or so through the year going forward. So that's quite an increase in our ability to get information to our members and other friends of the Society. I should also just do an acknowledgement of country. I'm actually sitting on the land of the Gadigal people of the Eora Nation, and I guess a national Zoom webinar presents a particular challenge for acknowledgement of country, but I would acknowledge the elders past, present and emerging on whoever's land you are currently listening to this broadcast on. Tonight we have a particularly relevant topic in a presentation. The question of Australian manufacturing and Australian innovation capabilities is a particularly hot topic, and I think the COVID experience has really focused people's minds on what the potential requirements are, and certainly the expectations of and the needs of, say, the medical sector have highlighted the need for a much greater focus on the sovereignty side of things and on what capability each nation state has, not just Australia. So we can expect to hear a lot more about this sort of issue over the next little while, 12 to 18 months certainly. So it's particularly good that Quickstep accepted our invitation to present, because Quickstep is one of the success stories in probably one of the most difficult sectors for an Australian company to participate in, which is the global aerospace market. And they've been particularly successful in delivering product for the J35 and the C130. I'll let the guys explain a lot more obviously about their product, but they are absolutely one of the examples we hold out regularly to our members to show that yes, it can be done in Australia. And I know if Mark Burgess was here, he'd say that's one of his biggest messages is yes, it can be done. And you guys are showing that it can be done. Mark Burgess, the CEO, sends his apologies tonight. He's actually travelling, which is an exciting thing to be thinking of at this stage. But he's very ably, we're very ably joined by two other members of the Quickstep team. Firstly, David Doral, who is the Chief Technical Officer and Head of Engineering for Quickstep. He works in two distinct overlapping areas of the business, shaping the company direction by researching and assessing technology. And he also looks after all their engineering resources, including the extensive engineering team. David did his undergraduate degree and master's at the Universidad Politécnica de Madrid, and he has worked in Europe and Australia with a variety of companies, including AirTech, an Airbus Tier 1 supplier, and MTORAS. And the list of programs he's worked on includes the Airbus A380, the 777, the A400M, and the Embraer 170. So a very accomplished global aerospace technologist. He's also joined by Krishna Oruganti, who's the technology and engineering manager. And Krishna is looking after the business by introducing new technology. And he began his career at RMIT in Melbourne. He also did a master's in mechanical and manufacturing engineering following on from his undergraduate degree. He worked mainly in the car industry in the first part of his career and has worked across Australia, North America, Thailand and China, and then found his way back into the aerospace world in the last 5 years and joined Quickstep. Again, a very accomplished global expert in the technology of manufacturing and production generally, and in aerospace in particular. So with that introduction, I'd like to hand over to the guys. And David, I think you're first cab off the rank, so
sure.
Over to you.
Yeah. So thank you, David, very much for your introduction and for the chance to present to the audience today the work that Quickstep has been doing during the years, the kind of company that we are nowadays, and where we are heading into the future, and particularly our experience around manufacturing innovation. As you've mentioned, Krishna and I work for Quickstep. I'm in a chief technical officer capacity, and he is a technical engineering manager. I overlook, as you well mentioned, David, the engineering team here in Bankstown, and also the R&D and technology development team in Geelong, in Victoria, where Krishna is based. Just to give you a little bit of an introduction of what is Quickstep and what we do. We can move to the next slide, please. Basically we're a composites company. We provide advanced composite solutions. So that's, our core market right now is defense aerospace. So mostly JSF and C-130. And I would say that JSF probably has the lion's share of the work that we do. We are also diversifying or trying to diversify into commercial aerospace, and we have some presence in other sectors. We've done some things in the automotive sector. Lately, we're doing things for other transport sectors like rail and even medical devices like portable X-ray systems. The core of our activity is manufacturing, fabricating composite parts, typically carbon fiber parts, but we may do occasionally some glass fiber, and also assemblies. And the typical assembly that we put together are the flaps for the C-130 that were turned or were transformed into carbon parts like 20 years ago. We build to print, so basically we provide manufacturing services to first tiers and OEMs. Sometimes we can build to a specification, and we also have the ability and the capability to develop new manufacturing processes. And that's, I guess, one of the areas that we've been trying to work on more actively in the last few years, and where we think that our innovation efforts and attempts are paying some returns. In terms of the size and I guess the magnitude of what we do, the revenue for last financial year was over 70 million Australian dollars. This year that we're about to close will be higher than that. We're a publicly listed company. We started in almost 20 years ago as an R&D company with our own proprietary technology that we'll talk about in the next few slides. Probably that was the focus initially, but we turned into a manufacturing business a few years ago. And again, the core of our activity and the one that is providing the returns and the revenues is mostly about producing parts for large military programs. We're a little bit over 250 people, mostly based here in Bankstown in Sydney, but also with a team in Geelong, as I mentioned before, and also a commercial office, commercial representation in the US, particularly in Texas. So I guess that in a few words, what we do and what makes us special is particularly our advanced manufacturing capabilities. I guess that is an interesting mix of activities and technologies, because we're combining high technology. We're combining the last composite manufacturing technology in terms of materials, in terms of automation, also with a little bit of craftsmanship, simply because the type of work that we do is not high volumes. We do many different parts, but not huge volumes of them, and probably we don't have so many opportunities for automation as you could find in commercial aerospace, particularly when we're talking about the best sellers like the A320, the 737, where they can do hundreds of aircrafts per year. In our case, we may do hundreds and thousands of parts, but from a very different or diverse mix. So again, we're trying to combine both the best of both worlds. And in order to do that, definitely we need to have a highly skilled workforce. because there's a lot of knowledge and a lot of know-how that is required to provide the quality that we supply to our customers. And from that point of view, I guess that we're very well renowned. Something also that makes us special, and that was the origin of the company, is our own curing technology, proprietary curing technology. We call it Cure with a Q, and we've trademarked also the brand AEROQURE as in an explicit application of Cure to aerospace and commercial aerospace. This technology, we'll talk about that a little bit later on, is an out-of-autoclave technology, and I guess that it brings or represents significant benefits. And that has been probably the main innovation component, or the main innovation result that the company has delivered. But in the last few years, what we've been trying to do is apply also that innovation culture to developing our own manufacturing processes, to automate some of those processes, to optimize them, and to come up with what we call this QPS 4.0 solution. That is also an interpretation of Industry 4.0 for our needs and with our own ethos and I guess cultural approach to that trend. Just a little bit about our plan. We've been growing significantly. We will grow again this year once that is closed. We have ambitious plans to keep growing. I have to say that probably this slide is right now under review in terms of where we're going to be in the next few years. Because our plan set up a couple of years ago was about doubling our revenues by 2024. We keep growing. Now we need to reassess where we are. It is true that we're relatively I guess protected in this current environment because we focus our activity in defense, and there is a sector or segment that is not heavily hit by the pandemic, and yet there may be some effects. Our key market is the US because our key programs are for American customers, as I mentioned before, JSF and C-130 Hercules. Defense is the core of our activity, but we're trying to get into commercial aerospace. And one of the things that I will try to do is to maximize the benefits and the value proposition of our own technology, our AEROQURE technology, particularly trying to target more international markets. Although, the reality, and I think that that was a figure that was shown before. Our production is basically, oriented or focused on international markets. So, talking about that proprietary technology, AEROQURE, as I said, is the trademark for our aerospace application to Cure. Cure is an out-of-autoclave curing technology. That means we don't need to make use of these large assets, these large pieces of capital equipment, autoclaves. And what we do is and we apply that pressure and that temperature rather than with compressed air or compressed gas. We do it with a fluid. A fluid that doesn't get directly in contact with the part, but as you can see in that picture on the top left corner, what we do is we lay up the laminate on a thin shell tool, and then we close this mold, that is the thin shell tool, and we close this mold so that that little pump that you see at the top, that is basically fluid resting there, can apply that pressure and that temperature in a very controlled manner and fast, quick manner to the part. And that's, I guess, the origin of the name of the company, Quickstep, because it was meant to provide the curing of that part in one step, in a very quick step. And these are probably the main principles of our approach. What we're trying to do, as you see on the top left corner, is to reduce the viscosity very rapidly compared to what you could see in an autoclave, and increase temperature accordingly. And that basically allows you to reduce the curing cycle, and again, in a very controlled manner, for instance, controlling any exothermal reactions, compared to an autoclave where typically you see long periods of ramp up in order to increase temperature and pressure accordingly, and make sure that all the air is removed out of the laminate, and at the same time you allow enough time to cure properly the material. So we do all of that, but again in a very compressed time. And we do it thanks to the heat and pressure transfer applied by the medium, that is in this case this fluid, and that through that bladder, that silicone bladder, allows us to apply both temperature and pressure. We do it also with a heat exchanger. So part of the technology is be able to control that rapid heating and cooling of the fluid with a heat exchanger that is automatically controlled by a SCADA system. And we do that again, very precisely and very rapidly. What you see at the bottom is the timeline that we've gone through, and actually we could even extend that to the early 2000s, but 2008 probably is where we started seeing a more industrial system. Main difference between then and now is that the original pressure at which we began curing parts was 0.8 bars. That was good enough for probably automotive parts in other sectors, but that wasn't enough for aerospace. So the kind of mechanical performance that you must see in aerospace parts wasn't possible with that pressure. So a few years after that, we realized that was the case, and we reached that, or we increased that pressure up to 2.5 bars, and that's the main difference that we've seen in the last few years. And I guess that the step change that has allowed us to offer and to show this technology to large aerospace OEMs and to attract their interest. In the middle, there are a few other, technical improvements, but I would say that probably that has been the major breakthrough that we've gone through, and that is positioning the technology in a place to offer again the kind of economics, while at the same time meaning mechanical performance that large aerospace OEMs require and demand.
If I may just interrupt for a second, there are a couple of question and answers that are popping up. They are relevant to some of the comments that you've just made, David. So I'm refraining from answering them at this point in time. We've made a note of those, and towards the end of this presentation, I'm happy to go through some of those question answers, if that's okay. So sorry, David, you can continue because they've been popping up on my screen. So sure. I just thought I'll let the guys know. Sure. You can continue to ask the questions, but we can answer those towards the end. Okay, so next slide, please.
Yes, to give you an indication, a graphical indication of how the system looks. This is not at a scale, so I would say that if we compare sizes, our AEROQURE system would be even smaller, more compact than an autoclave. But yeah, you can see a little bit the shape of the. In this case, we would have two AEROQURE presses in parallel, and they more or less represent the size, or at least the shape of those presses. The elements to the right are mainly the heat exchanger unit that allows, as I said before, rapid heating and cooling. Next slide, please. And trying to explain where do we sit in terms of technology and what AEROQURE is compared to other curing technologies. If we divide very generally curing technologies between open mold and closed mold, we would be at the top together with press forming and RTM. We typically see in aerospace open mold technology, so mostly autoclave. That has been the technology of choice, the conventional technology, and the one that is mature and that we can see in basically every single aircraft that is flying at some extent. In the last few years, companies have tried, or big OEMs, large aerospace manufacturers, are trying to move into out of autoclave technologies, simply because they probably allow higher rates and more flexibility. We're starting to see in Europe and in other places liquid resin infusion, and there are a few, I guess, very relevant parts already flying done with liquid resin infusion. And yet, what we think is that the rates, the high rates that aerospace is going to need in the future, particularly when we're talking about single aisles, for instance, will be provided by closed mold technologies. RTM could be one of them, and actually we have our own experience with that, and Krishna will be speaking about a use case based on RTM. But AEROQURE is our own value proposition, our proprietary technology, and where we think we can offer the right mix between, again, mechanical performance and economics and rate of production. We see also that thermoplastics will be one of the technologies of the future, whether it's with autoclave, in situ consolidation, or press forming. We feel that probably they're a little bit behind in terms of maturity, although we know that there are already thermoplastic parts in flight, so to speak. But yeah, as you can see there, we think that AEROQURE is going to have a bright future, particularly here, and probably in the next slide we can see how that is going to happen. So if in this diagram we see how those technologies are placed. We see that AEROQURE could be in the sweet spot in terms of volume and in terms of cost. In terms of volume, because obviously it's not we won't be able to reach huge production rates over tens of thousands that you can see with high pressure RTM and more conventional compression molding that you could see in other segments, in other sectors. But definitely we are way faster than the typical autoclave technology. And our numbers and our original or our initial tests and all the work that we're doing suggest that we can go definitely over hundreds of parts per year. We think that we will be very comfortable reaching production rates of thousands of units per annum. And all of that done with very contained manufacturing costs, definitely lower than autoclave. And again, I insist, meeting the mechanical performance that you require, that you demand from aerospace applications. All over to you, Krishna.
Thanks, David. So, a lot of that information that David just presented is the backbone of Quickstep's, I would say, innovation pillar. We are an innovative company, but in order to understand innovation in general, there are two aspects that you need to think about. On the screen, you actually see on the top left corner, you see a number of organizations. So the key difference here is between the top and bottom is the companies such as Sony, Amazon, LinkedIn, or Tesla. They're all product-oriented or service-oriented company. So the primary focus is on a particular product and skills and the knowledge and the systems that go in delivering that particular service or supporting the delivery of that product. Whereas the companies at the bottom, like Netflix, Philips, Vanguard, Ford, they're all process-oriented companies. Now, while they do have a certain innovative product or an offering, they don't really focus a lot on those, or they emphasize more on the processes that enable the delivery of that particular product successfully or effectively. Now, Quickstep is a process-oriented company because implementing measures and taking the corrective actions are percept in this particular instance for an organization or an aerospace organization like Quickstep. Now, what is innovation? So you can kind of sum up this in a couple of, I would say, analogies, but the one that we've been quite commonly using in the organization is something like this, where you take in an unsolved problem and then, or a series of problems, and then you kind of move towards a solution over a period of time. Now, when you start, you have a less structure, there are lots of unknowns, or there are lots of ambiguous, I would say, statements or assumptions in the mix. Over a period of time, you then convert them into more structured, known, clear deliverables, which form part of the solution. Now, that means you're moving from disorder to order over a period of time. The trick here is to understand the asymmetric nature of innovation. If you fail at the start, the stakes are low. But if you succeed, it's a flash of genius because the expectations are low. But over a period of time, if you then carry forward that innovation, or if you carry forward that conversion of those less structured ideas and then ambiguous thoughts into more clear ones, you're actually putting systems and processes in place, which will then mean there are high expectations and success towards the end of the journey is expected. Failure there, that means stakes are very high. So the trick here is to understand the balance between disorder and order, and then learn to fail fast and then move ahead. So innovation in this case is basically, I would say, organizational creativity that's converting unstructured known into predictable outcomes and then driving effective and efficient rates of success. This is something that we use fundamentally within our organization. And there are again three other, I would say, major pillars that actually hold this whole thing together or to nurture this. In order to have an efficient and effective innovation model must employ the teams to be able to generate relevant ideas. They must be able to select and align them with an organization strategy, and that's very key. So the organization must actually have a very clean and a clear organization, I would say, goals or vision, which is then executed with a solid project management team. So all of this together, if working in parallel, provides an efficient and effective innovation. So something which started within Quickstep was a journey that I can talk about a little bit over here. Originally, as David mentioned, Quickstep started off as a technology company in 2001, focusing on an out-of-autoclave technology for composite curing. A number of patents and innovative advanced manufacturing methods have been developed over a period of time, but if you compare the success measures, or if you look at the drivers that have enabled some of those success measures to come, would be all the different projects that have matured over a period of time. So you can see here that small teams, incorporation of appropriate quality measurement systems, the philosophy of design thinking, technical bottom-up approach. So these kind of, I would say, pillars have actually been embedded within the culture of the team here, and transforming and maturing the technologies further to deliver these particular projects. The 6-segment approach, where we find a strong commitment and leadership. Sorry, I'll just have to minimize the video. Yeah. To reinforce the innovative traits, empowerment, which is basically allowing the teams to contribute towards the context, finding opportunities, identifying them, and continuously improving them, and allowing the teams to do that. Working fast, moving fast, agility, and creative heat. That means joining forces and spreading, the ideas and brainstorming them throughout the business, and incorporating all of these things back into the vision and roadmap for both internal as well as external is a continuous cycle that is looked at within Quickstep. In terms of the technology roadmap, we've identified a number of focus areas, as you can see here. Typically for any composite manufacturing company, the process that you see on the top, which goes from materials, converting those materials into usable shapes, or I would say kitting, laying them up onto tools, and then curing them using heat, pressure, and time, and then followed by inspection, trimming, and painting, which are the downstream processes, are pretty standard. So in terms of Quickstep's technology focus areas, we are looking at each one of them individually, and then trying to do a value stream map to identify which ones will provide an effective, I would say, value proposition to help meet the business goals and objectives. The Industry 4.0 or QPS 4.0 is basically taking all of these things into a common bag, and then using digital tools in order to facilitate an effective solution is what we're actually trying to work on. So one such case study is the F-35 flare housing tube. It's a composite flare housing tube. This was originally designed as a build-to-print product, but then later on, it was provided to us, and then we had another look at it. So this is where we did a bottoms-up approach. Originally, we had the defined design and process requirements specified. Then that kind of led into the process engineering, manufacturing engineering, and production engineering related sections. The defined design and process requirements basically describe what needs to be made, or this is the technical drawing in question. The process engineering functions basically tell us what and how the product needs to be made. And the manufacturing and engineering deliverables kind of dictate where it's made, who it's made with, and with what tools these particular products are made with. So when we cascade these things across, the information that was provided to us was essentially a technical drawing. It said what needs to be made. In this case, it's a flare housing tube. But everything else was somewhat left a little bit open to us. So the key difference here, where we were dealing with this flare housing tube, is a build to specification, where what was given to us, how, with, and when is what we actually chose to deliver the lowest cost possible or the most effective design. And we use technology as an enabler for doing this. One key thing was to understand the critical design needs and deliverables. And the starting step was obviously to understand what is involved, or to understand the technical drawing. So we analyzed the current design, we optimized it for cost and performance, and then value, and then we even looked at, I would say, an initial business case to identify the key bottlenecks, labor requirements, and then come up with, I would say, a high-level macro process flow, which was used to run a simulation and then come up with a rapid prototype to prove the concept. Now, this cycle is part of the continuous improvement cycle that you keep going in circles to identify, those various points where you can fail fast. So the principle that we adopted here was learn fast. If you have to fail, fail fast, but then apply the knowledge back into the business case to see what you can improve and then optimize. So after a number of these cycles, we ended up with the basic outflow of how it needs to be done and what are the different tools that these things need to be made with, and what is the associated cycle times, which will then provide the lowest cost possible. Because cost was a major driver for us, so we applied a commercial engineering model in order to optimize this particular design. And we integrated all of that using digital travelers. Now, for those of you familiar with the aircraft industry, traceability is an underlying fundamental. The digital traveler is basically moving away from a paper-based, I would say, sheet into a digital traveler, but more about trying to create that passport that can go across right from the source of the materials till the finished product in assembly, and trying to integrate all the services and the processes to be aligned with this. So it's a subset of the Industry 4.0, I would say, initiative, but this is something that we embarked on with this particular project. At a macro level, this is what it kind of looks like. So we have the systems on the right-hand side, such as the analytical systems, such as CAD and CAE, and then the operating sections, such as the standard operating procedures, curing parameters, or trimming programs, and integrating all of those into the physical equipment, and then trying to control it through some sort of a central database. In this case, it could be a SCADA system. So this is what we've actually, this was our vision. And then when we originally started this, I'll probably take you through this particular slide here. So when we originally started the concept for this particular process, there were a number of process steps to which we had a particular intent. So we wanted to actually go and describe each of these process steps and said, what do we really want to achieve out of each of these steps? And what are the deliverables? What are the objectives? When we looked at it from a bottoms-up approach. So when we first put the concept together, the maturity of the ideas were very, very low. So they were, you can see them, like, you know, there were a number of, I would say more than 95% of the elements were unknown to Quickstep. Quickstep originally only ever made products out of an autoclave or using infusion, but never in an RTM scenario. So introduction of an RTM technology to Quickstep, or an integrated RTM technology to Quickstep, was something new at that point in time. But as the program matured through, there were a number of these deliverables that moved into a maturity phase at different rates, but more focusing on the fundamentals of commercial engineering, and then saying, okay, how do we actually drive the cost out and then get the best value out of money? And towards the end, where we are right now, this was basically, I would say, an 18-month journey from intent till, I would say, delivery, where we've matured probably more than 95% of the deliverables within the project. In terms of the vision, was to actually have an automated, you know, somewhat free, I would say, one-piece flow arrangement at a high level, but then we ended up converting that into reality that you can see there. We have an automated ply cutting, sorting, material preform, and inspection prior to the resin injection as a one-step process, which integrated, I would say, 4 or 5 different steps in this schematic. And then the integrated resin transfer molding is something new, and we're actually working on the next level of integration on that for process control and process monitoring, which is, you know, which is still in development right now. That's all I had to present. Over to you, David Cox or David Atkins.
Yep.
I might run through some questions now, if that is okay with Krishna and David.
Sure.
Sure.
Go ahead. Far away.
I think you've got the questions. Do you see the questions in front of you?
Yeah. So if you want, I can take the first one. The C-130 flap design was originally developed by Hawker de Havilland Bankstown. Have you sought to adapt the design incorporating any of Quickstep's innovations with the OEM support? I have to say that probably, as far as I remember, we didn't try with the C-130. We tried that with F-35 parts, and that was an effort that was undertaken a few years ago. I have to admit that back then, what was proven was that the technology wasn't ready. I mentioned before that one of the significant changes, significant improvements that we've done in the last few years is increasing the curing pressure, going from 0.8 bars to 2.5 bars. When we did those tests, and when we tried to show what we could do and how could we do those parts with the AEROQURE, again, the pressure was lower. We couldn't reach some of the parameters required to meet the mechanical performance, basically the mechanical tests or things even like, void content that would be required for such a part. And unfortunately, we didn't go any further. A few years have passed since then, a few significant improvements we've made, particularly the curing pressure. Right now what I have to tell you is that we're working on doing something similar with OEMs and with first years, global OEMs and global first years, to try to qualify the technology for aerospace parts. So I guess that I can tell you that we're right now in the middle of that process.
Okay, the next one we have from Alfred. Have you applied the AEROQURE process to RTM resin infusion molding?
I'll take that, David. The answer is yes. We have done some, I would say, initial level development activity on this a couple of years ago. We haven't really commercialized that as such, but it is more at an R&D level. There are quite a few challenges that we actually faced while doing that early on, but then that was with our previous generation system. But now we've actually matured in. So it is actually on probably part of the development that we'll be working on right now.
Okay, next question's from Don. Do you think your process can be extended to accommodate a resin infusion approach?
Yes.
That would be the same. Yeah.
Okay, the next question from Sam. For innovation, how do you decide how much time and effort to give to an idea before letting it go? Because if one person has an idea and has 1 week to develop it, it may fail, but possibly if that same idea was given a team of different people and more time resources, it might eventually become a good new customer production ready innovation product. However, could you give an idea of all the resources in the world and it doesn't develop into a useful, beneficial product?
Yeah, I guess that, yeah, I'll try to give it a go, but yeah, probably Krishna also can talk about that. I guess that, yeah, that's a very good question and tricky one to answer. I guess that part of the process is to try to rapid prototype as much as you can to see whether there's some merit in that idea. Another thing is try to get some input from the customer or potential customer as soon as you can, so that see whether what you're proposing can have any practical application. But it's true that something. I mean, at some point you need to make a decision. I have to say that in our case we have I guess a very I would say compact but agile technology development team, and that's the team that Krishna leads. It's been, I guess, very dynamic in order to prove something, run it through a few different cycles and try to see whether it works. At some point, we need to make a strategic decision to cut it off. But we try to use all those elements: rapid prototyping, customer feedback, and also obviously it needs to be aligned with our strategy. But again, I guess that is part of also of the learning experience. And I would say that maybe in the past, we've taken things a little bit longer than we should. That we should have killed off, a little bit earlier. But that's part of the learning experience, I would say.
I'll probably add a couple of other notes to that, David. So the key thing here is to fail fast or to rapid prototype. So those keywords would typically be used in smaller teams. So in order to actually understand innovation, we need to understand the difference between innovation and invention. So if we said that we had all the time on the planet and then we had to come up with something new, you would probably come up with something new. But if you want to innovate, innovation is not invention. It's not like creating something brand new. It's like trying to optimize what you've got and then trying to make it better. Now, it is true that if you can break down a complex problem into smaller problems, it is easier to solve. So similarly, what we tend to do is, if you take in a holistic approach of a particular idea and then try to break that idea into smaller sections and then divide them, you will then quickly identify the areas or the ideas or sections of the idea that are easy to validate. Now, those are low-hanging fruit, and then you just go and do that. So the allocation of time for that would be largely project-driven, or they would be mostly around I would say the objective of the organization or the customer's requirements. But there will definitely be some sections within some ideas which will truly be new, and that's a new way of doing it. Now, that's when we will have to assign more time to it and then divide that team out and then run them in parallel. So this is probably not a very easy question to answer. There's no straightforward thing to this. It really depends on, I would say, multiple scenarios, but the key model is the believe, think, behave, and then act model that kind of drives with this. So if we believe in a particular, if the team believes in a particular idea and they work through it, they need to be able to spread that, or they need to be able to provide enough data to be able to build that credibility and buy that additional time as required to keep that idea game progress to the next level.
Okay, our next question is from John. Have you employed Industry 4.0 throughout the factory example to legacy production lines with old equipment?
It's in the plan. I'll take that, David. It's in the plan. We are working on that particular front. It is not a simple, straightforward solution. There are many, I would say, intermediaries that need to be resolved. Older equipment comes with, I would say, lots of legacy systems, which may or may not be compatible, but we are working on that right now.
Okay, another question from Sam. Are there any benefits to the qualities, properties of the final product material using your method instead of traditional autoclave methods?
I'll take that one probably. I would say that right now, what we're trying to do is to match the mechanical performance and the typical qualities or the required properties of any aerospace part. So what we're offering is a faster process, is more economical. So in the end, yeah, beneficial for the OEM, for the integrator. There are things like, for instance, curing with cores that whether it's a foam or a honeycomb, that the fact that we use a lower pressure could benefit and yeah, could pose a substantial advantage in terms of you won't see that much or that many parts being damaged or with crash cores. But the reality is that those parts will never make it to through the quality process. I mean, from a point of view, I guess that good cured parts with autoclave will be very similar to the ones that we can produce. If anything, the rate of scrap parts, so to speak, it should be lower with our system. But again, you know, what we're trying to do is the same, but more rapidly, faster, and cheaper.
Okay, thank you. Another question from Don. You've mentioned defence, commercial, aerospace applications. Are you looking at all for space applications?
I would say that probably one of the limitations that we may have. I mean, I think that it could work for some space applications. One of the limitations that we may have is that our technology is, as we mentioned before, a closed mold technology. Probably is not ready in its current form for very large parts. So if we're talking about a very large launcher with some sort of a cylinder or fairing or a very large part, probably we wouldn't be ready for that yet. If we're talking about smaller parts, yeah, why not? So it will depend on the application, but I would say that probably the main limitation would be size.
Okay, thank you. And we've got a question from John. Why is the technology development team located at Geelong rather than at Bankstown?
Okay, so I guess that one of the reasons why we wanted to have a dual presence was, you know, have also presence in the state of Victoria, and I would say that probably, and Krishna will be able to explain this better, but I would say that what we set up that facility was first integrated within the Deakin campus in Warren Ponds, and trying to tap onto a lot of I guess spare capacity that was left once that the automotive industry in that part of the country started to go away, and there was a lot of talent and a lot of technical capability that was there, you know, and actually Krishna is probably one example because he comes from the automotive industry. We also try to do some work there, and we have had some technological successes trying to do using our technology for automotive applications. Probably because of our strategic focus now, we're working mostly in aerospace, but that's also an area where we use AEROQURE. And again, probably the combination of both, another state close to Deakin and a big campus with a lot of composite manufacturing or composite technology, academic and research capability, and tapping on that resources led by the automotive industry probably are the main reasons.
And just to add to that, David, it's mostly because we're part of the carbon cluster. So in Deakin University, Vaughan Ponds campus, there are a number of carbon fiber manufacturing companies like CSRO. We've got Carbon Nexus, we've got Uphill, we've got Carbon Revolution, and then we've got Quickstep. So essentially, it's part of the carbon cluster. So there's a lot of combined knowledge and experience locally on the site as part of the Deakin campus. So we can all benefit from that by collaborating.
Okay, thank you very much. We might leave the questions there, and I'll just hand over to David for a close, and thanks.
Thank you, David, and thank you to our panelists. I would just like to propose a vote of thanks to our panelists tonight for their contribution. I think it really was a double-barrelled sort of approach. First of all, you've got a unique technology which has been developed here in Australia and is now being commercialised, and that is always pleasing to see, and it's just great to see that technology being explained to us so clearly and simply. The second barrel, though, was probably the one that's got as technologists, we always think the technology is the hard part, but I think what you were able to show tonight, it's actually the smarts that sit around that, the production system, the process engineering that goes on, is where a huge amount of the effort has to go in if you're going to be successful in a global game like this. And I thought that that was actually a great message for us to show just what's required in the innovation space to stay ahead of the game and to actually deploy these technologies like the innovation you've got into a successful product, or successful capability, I should say, that produces a product. That was very well illustrated, I thought, by the example with the flare tube. And the nice thing you showed there was moving up the food chain from the build to print to the build to spec. And eventually what you were able to do is come back and effectively say to the provider, hey, here's your product, but we can do it better and cheaper in this way. And that's demonstrating that escalating capability that you were aspiring to with your process and design thinking approach. Lots to learn, lots to meditate on, but thank you both for demonstrating what it takes to be a successful player in a global aerospace supply chain these days. Thank you. I'm not quite sure how we do that. Normally you get a round of applause at that point, but I think you can assume a round of applause has ensued. I just have a couple of quick housekeeping things. The branch AGM is on, again, digitally on the 24th of June. I would encourage any members listening to tune in on that. It'll be a relatively short, straightforward meeting, but please tune into that. As I mentioned at the beginning, we have an aspiration to get a webinar to you about every 2 weeks. And so the next one will be hosted by our Melbourne branch, and it'll be an Air Services presentation on the 17th of June. So watch out for that. We have also a presentation coming up from our Canberra branch a little later on military aircraft production. And on the 6th of August, we will have Mel Hupfeld talking about the RAAF centenary. And so that's one to look forward to and mark in your diary. So keep your eye out on the newsletters to pick up the links. But I'll close by saying thanks again to our panelists. It's been great hearing from you. Thank you everyone who tuned in, bearing with us. It's our first time out. We're nearly home, and so far the dog hasn't kicked the lead out or anything like that yet. So thank you for joining us, and look forward to hearing from you next time. Thank you.
Thank you, David, and thank you to all the audience.
Thank you, everybody.